So it looks like it is 9:45, so time for us to get started. So I want to welcome everyone to the Computational Mathematics 1 session this morning. And our first speaker is Mikhail Kenner from Western Kentucky University, and he will be speaking on a coupled PDE's model of surface and composition dynamics in applied electric fields. So you can go ahead and get started. Thank you.
Thank you, Mark. Thanks for the introduction. I will describe this model, which is quite old now. I did this with my master's student Mahdi Bandegi in around 2014-15. So since then it evolved quite a lot, but we did some useful stuff here. So it's not that complicated yet. Now it is very complicated. So this is fun to describe and watch. So basically, why we are modeling thin films, because thin solid films are in every micro and soon nano device, such as light emitting diodes, thermal actuators, transistors, and optical waveguides, to name a few. And for all of these devices, for them to function properly, there has to be a control of surface morphology, in other words, surface shape, and also composition, because most of these films are alloy films. Most popular control in these applications is by a constant electric field, or by equivalently the direct current. The effect of the current is that it induces the electromigration of the surface atoms. I will describe electromigration in a second. It's an interesting effect. The electromigration and natural diffusion on the surface in the high temperature environment dynamically changes the surface shape, and for a multi-component film, as is our interest, it also dynamically changes the surface composition. So it is our interest to describe the coupling of these two effects mathematically and see what effect the morphology change has on composition and vice versa. The electromigration is the effect that was discovered roughly 70 years ago. Essentially, the simplified picture is like this. Imagine that you have a metal conductor, for instance, a copper conductor, and you apply the constant electric field to this conductor. This, of course, induces the electric current through the conductor. The current is from anode to cathode, which is the direction of the current is from right to left. However, the electrons move in the opposite direction from right to left. The current is from left to right. And when the electrons are moving through the conductor, they scatter on the atoms of a metal and transfer their momentum to the atoms. And therefore, first off, the atoms become charged, they become ions. And second, the transfer of momentum pushes the ions to the right, towards the anode. Without transfer of momentum, these charged ions would move in the direction of the electric field, which is from left to right. But this electron wind, as it is called, it overcomes the electrostatic effect and pushes the ions in the opposite direction. So what are the applications of electromigration? There are plenty. Some of the most interesting, at least for myself, are the roughening of a surface by electromigration, which is the formation of a hill and valley structure on the surface, as you can see. This surface relief, it has the characteristic length scale, obviously. Essentially, it's a periodic structure, although in reality, it's not strictly periodic. The period changes from point to point along the surface, so to speak. And these hills, they have quite a large height, as you can see here, and in the scanning electron microscope or atomic force microscope, they can be clearly observed. The application of this effect is, for instance, to assemble the pattern of molecules or atoms which you can deposit onto the surface, and they will assemble into the valleys, obviously, of the surface relief. And when this can be used for medical purpose or for whatever other purpose one can think of. Another application which is very recent, and there is a lot of research in that, is the creation of nanocontacts by electromigration. Here, one has two very thin metal films. One has a continuous metal film, like silver film, deposited on silicon. And when in a controlled fashion, one can break this film in two parts by applying electric current. And this way, the nanocontacts are formed, and when one can, for instance, deposit a single molecule between these contacts and pass the electric current and measure the properties of this molecule. And interestingly, by reversing the current, one can controllably close this nano gap and then break the film again. So this is the reversible process. And this is very complicated, and it is not modeled here because this geometry is clearly very difficult to model, while the infinite geometry of the film surface is fairly easy to model. This is why we are focusing on the first application here. Now, to get closer to modeling, this slide explains the effect of the applied electric field. Imagine you have a two-dimensional situation, which is a film surface is represented by a smooth curve, h of x, in the plane. And this curve will evolve in time because the shape of the surface changes. Now, what would be the effect of the electromigration here if the electric field is from right to left? Then it has the component which is uphill on the surface. This means that the electron wind is downhill, which is the surface atoms get pushed downhill by the electron wind. And therefore, the hill in time will become smoother, and in the limit of infinite time, so to speak, the surface will become planar. On the other hand, if the electric field direction is the opposite from right to left, then the electron wind component will be uphill, which is the atoms will be pushed from the valley to the top of the hill, and this way the film surface will become rougher. So this is the origin of this hill and valley effect, which is seen in the left panel on the previous slide. And so we formulated the model for the formation of this hill and valley structure for the bicomponent film, which is for the metallic alloy. For instance, a very common alloy is iron gold alloy. Let's say Ca is the composition, is the concentration of gold atoms per unit area, when Cb is the concentration of iron atoms per unit area. And since the sum of Ca and Cb is 1, we need to only model the dynamics of Cb. Okay. So here we have the set of two coupled parabolic type partial differential equations. One equation is for the function h of x and t, which is for the shape of the surface. And second equation is for the function Cb of x and t, which is for the composition of iron on the surface. These equations are very heavily nonlinear, and they are coupled, which is there is a two-way coupling between them. The first equation is fourth order in space, and the second equation is second order in space. Second equation for Cb is essentially a nonlinear Fickian diffusion equation with the electromigration effect accounted for through this parameter capital F, which measures the strength of the applied electric field. This F here is, of course, Chim's concentration, and then there is differentiation. So overall, this is the second order equation. The first equation for the shape is the fourth order equation because it contains the curvature of the surface naturally. And the curvature is, as we know, proportional to the second derivative of h. Therefore, this is the third derivative term here, and there is another differentiation making it a fourth order equation. Other parameters of notice here, and all parameters here are purple, except the electric field parameter is this anisotropic mobility function, which is actually not a parameter, but a parameter function, so to speak. This function is a function of the slope of the surface, hx, okay? And beta here is the strength of the anisotropy. Why does the anisotropy come in? It comes in because the film is a crystal, and therefore diffusion is anisotropic on the crystal surface. So our goal now is to make the analysis of this system, and we did not try to do anything sophisticated as far as analysis. And also we will want to compute, of course, the evolution of H and the evolution of Cb. As far as analysis, it is easy to notice that this system has the equilibrium state, which is H equals 1 and Cb equals a constant. H equals 1 means the surface is planar, which is just flat. And Cb equals a constant means that the composition is a constant. And so we are now trying to analyze the stability of this equilibrium state with respect to small imposed perturbations of H and Cb. These perturbations in reality have a thermal nature. Whenever the temperature is non-zero, there is a thermal perturbation of the equilibrium. And the question is, will it decay or will it grow? If a perturbation will grow, then potentially it may self-organize into this hill and valley pattern. Okay. What we do then is we represent H as equilibrium value plus small perturbation C of x and t, and we represent Cb of x and t as the equilibrium value, certain constant Cb naught plus small perturbation Cb hat of x and t. We substitute these variables into a system and drew a multivariable Taylor series expansion essentially, and retain only the linear terms. In other words, we are linearizing the system with respect to these perturbation functions. We also need to linearize the mobility functions in order to make it all consistent. So we linearize the mobility functions with respect to mobility values on the planar surface when hx is 0. Okay, so m of 0 and m prime of 0 are two numerical parameters which we can choose. Okay. And after this has been done, when we take the so-called normal form for the perturbations, we represent each perturbation as a wave with a wave number k times the time-dependent amplitude, where this amplitude is the product of a constant which we don't know right away, we need to figure it, and the growth rate factor, e to omega of k times t. And similarly for the second variable here. And so the goal is of course, to find for which values of k this growth rate will be maximum and positive, okay? This maximum value of k, which delivers the maximum of omega, will be the one which will be seen in the experiment, because that perturbation will grow the fastest. And so it would be this wave with that wave number, or equivalently wavelength. Wavelength is essentially the reciprocal of a wave number. It will be this one which will be making our hill and valley structure. Okay. So we did this, and we calculated the dependence of the reciprocal of a wave number, which is the wavelength, or you may say the period of the wave, as function of various parameters that enter our system. And of particular interest here is the dependence on the strength of the electric field, of course. And one can see that this lambda max is inversely proportional to the square root of the electric field strength. So when the electric field strength becomes larger, the wavelength becomes smaller, and our hills become more densely, more dense on the surface, which is where surface density becomes larger with the increase of the electric field strength. And the growth rate, on the other hand, is proportional to f squared. So the larger the f, the larger is the growth rate. Okay. So this data is helpful to experimentalists, of course, because he would like to know what effect the applied electric field strength would have on this surface pattern. Okay. And next, we computed the evolution of the surface from our nonlinear system. We took the random initial conditions for H and CB around their equilibrium values, and you can see how from small perturbation of H, this hill and valley pattern forms with time, and how it becomes coarser with time, which is the scale increases. And the composition also changes, starting from uniform composition under this set of essentially governing parameters, where CB becomes smaller, meaning that surface becomes richer in gold atoms. All right. If we take the different values of these mobility parameters, then on the other hand, surface becomes richer in iron atoms, while the hill and valley structure still forms. There is actually a marked difference in the time scales and length scales here. The hill and valley structure looks roughly the same, but the analysis shows the clear difference between the characteristics as they evolve in time. Okay. On this slide, and I need to finish, I have only a few comments left. On this slide, we actually measured this mean distance between neighbor hills, Lx, as function of different parameters and as functions of time. I want you to check only this top left figure. You can see here that as the electrical potential becomes larger, that is, as the field becomes stronger, Lx becomes smaller, okay? So larger field means more closely spaced hills on the surface, okay? And of course, we quantified all these dependencies, that is, we fitted them with power law functions to make clear what the powers are in these fits, okay? Like here you can see that changing the applied potential, we have the increase of the power of T from I'm sorry, the decrease from 0.138 to 0.074 when delta V changes from 0.01 to 10, okay? And so this is all I wanted to say. Thank you very much.
Okay, thank you. Any questions for our speaker?
This is a stupid question.
Okay, I was going to ask it. So you're talking about modeling this over a large scale surface. Do you do any? When I noticed the basically in the quantum side, it would correspond to the multi-well structures. So I mean, do you do any analysis there of the current or the current propagation across these surfaces for, like in the case of device physics or anything?
No, no, I don't do that. This is not my area at all. Yeah, I understand what you are asking about, but no.
Yeah. I remember when I first saw what they used to call the VSSCF, the variable space superlattice energy filters, back in 1988 at Georgia Tech. Chris Summers and his group at the Georgia Tech Research Institute they had come up with a very simplified analysis, not at all like that, but it was just basically coupled systems of the multi-wells and solutions in terms of area functions. But your thing is, I can see it's into much more depth.
Yeah, my thing is this continuum macroscopic modeling of essentially nonlinear diffusion and morphology evolution. Yeah. I would like to branch into something more quantum-like, but I need collaborators for this to begin with, right? To teach me something to begin. So not yet there. Yeah.
On these, on the dynamics of these heights, your little h function that you cite for there, and the CB, some of the boundary conditions, are there the boundary conditions that are dependent on the boundaries of the flow as it itself develops? So the nonlinear boundary conditions depending on the shape itself. The shape evolves as a function of itself.
Right. Yeah. So in this model, the boundary conditions are simply periodic because we take essentially infinite surface and impose periodic boundary conditions so that they do not interfere with the dynamics at all. Any boundary condition which is not periodic will have an impact on the dynamics, and such boundary condition needs to be carefully physically formulated. So here we do not attempt to do this. But yes, you are right. Yeah. In reality, of course, all films are finite, right? So you need to impose the boundary conditions on the edges of the film. Correct. Yeah.
Do you have graduate students or undergraduates or Gatton kids that are working with you on some of these aspects of this?
Not presently, no. I did. I hope I will have a student again and more, but not at the moment. No.
Well, some excellent research, man.
Well, thanks. Thank you. Hope you liked it. All right, Mark, back to you. Thank you.
Okay, well, thank you. So let me go ahead and introduce our speaker and the topic. So our next talk is by Ethan Kelly. This is on graphical assertion of the validity of an analytical Hodgkin Huxley model solution. So you can go ahead and proceed then. Okay, I don't hear any sound.
You're muted, Ethan.
Sorry about that.
Okay,
Let me see. Can you all hear it now?
I can hear you, yes. Mhm.
Could you hear the video playing?
No.
No.
Oh gosh. Huh. Well, I guess real me is gonna have to take over.
Yeah.
Okay. Well, here we go. So this is my presentation on a graphical assertion of the validity of an analytical solution to the Hodgkin-Huxley model. Yeah. So most of you know that a nervous system is an expansive network of neurons sending electrical signals back and forth. These electrical signals create very complex behavior, as we know in humans, and it's quite useful to be able to model such a thing. So back in the 50s, which actually, you know what, never mind, I'll get to that. So the movement of ions into and out of the neuron create the electrical signal, which is called an action potential. Ions such as sodium and potassium, those are the main ones. And in 1952, two really neat guys, Hodgkin and Huxley, they introduced their model for action potential using giant squid neurons. And they specifically used giant squid neurons as they were quite large, and it's easy to probe them to get some data from them, which is very important for creating a model. And their model, which is a set of differential equations, is aptly named the Hodgkin-Huxley model. So a bit more background knowledge. For many years, people have tried to solve these equations. They're a bit finicky. Numerically, trying to solve them produces some explosions in finite time, which is never preferable. Analytically, people just didn't really know how to find a solution, didn't know where to start. So back in the 80s or 90s, I believe, two guys, Marouse and Alkaby, managed to come up with this equation, which is numerically stable. And you can see it here. Pay very close attention to the -1 over theta squared dt squared term on the left side of the equation. This will become very important in a second. So my research mentor, Dr. Tony Simpao, he discovered that attempting to solve this equation without truncating that -1 over theta squared dt squared, which is often done for simplicity, people believe it would make it easier to solve. However, the contrary is true. By leaving it in and not removing it, it's actually quite easy to solve using standard methods of ordinary differential equations and the Lagrange inversion theorem. So here on the right, we can see some of the original Hodgkin-Huxley equations. We have the current in terms of a whole bunch of stuff. You have the what are called N, M, and H terms. These are terms I'll discuss later on, but they basically relate to the ion movement, modeling that. But these equations, quite difficult to solve on their own. The Marusan-Alkabe equation helps a lot. However, the key piece to this, I think, is modeling it as a transmission line. This really helps a lot, as my research professor found in his paper. And by modeling this, the neuron as a nonlinear transmission line, solving it is possible using, as previously mentioned, ordinary differential equations and the Lagrange inversion theorem. So some of you may be wondering about that, the -1/θ² dt squared. Why do people leave that out? What is the, besides just a mathematical motivation, what are the physical implications of leaving that out? Why would you want to include it? And we need to discuss what theta actually is to kind of wrap our heads around this. Theta is the wave speed. Waves have a speed, obviously, and it's very important to note that waves generally don't have infinite speed. That's a pretty important thing to know. And leaving this out implies that something here is zero. Obviously, on its own, the second time derivative will exist of voltage, which implies that 1/θ² is zero, which then implies that theta is a very large number nearing infinity. That's the only way you can get a zero from 1 over a number, at least in this case. And that would imply this is very large. Infinite wave speed. Doesn't make any sense. This also relates to the inductance factor of neurons, which has been quite difficult to find. That's one of the few factors of the neuron which weren't found in the original paper, I believe. But anyway, that's just the physical motivation for leaving this -1/θ² in. So going on, my professor, by including the second order time derivative, the equation was easily solved, as you can see. However, it produced quite a large result. This thing, it looks very beautiful, very elegant. We have the current in terms of the voltage and the voltage in terms of the traveling wave variable mu. And this was done using the Lagrange inversion theorem, which I'll discuss that and its effects on the Mathematica graphs in a second. But these are the equations. So back to those N, M, and H factors. As I mentioned, those are used to model the ion movement to find the current and voltage. So we have N, M, and H. You can see the graphs and you can see the functions. Now, if you're observant, real quick with math, you might be able to see that something's a bit fishy at certain points with these graphs. For example, at v equals 10 here, you get 0, e to the 0, -1 + 1. That gives you 0. You get an indeterminate form here, basically. And that's not good. Now, on its own, thankfully, Mathematica has things for finding limits at points. But there's some issues raised because we're not just trying to find the values of this. We're going to be taking the derivative of this. And on the next slide, you'll see that some pretty bad stuff happens if you just mindlessly take derivatives. So by performing the Lagrange inversion theorem, a very significant part of it is this, taking the derivative of the variable minus a constant over a function of the variable to the nth power. So basically what you're doing is you're amplifying that indeterminate form. You're basically making the point discontinuity affect everything around it. And at smaller values, that's not too bad. At larger values, however, it starts to get very big. And being that this is an infinite series, that just won't stand. That's not useful. You can't really verify anything if your graph just looks like this. So this is the 3 lines of mathematical code that are most important to getting the result, the implementation. And being that at larger values, this kind of breaks down, it's, in my opinion, far more important to look at something that provides information on the form, being the factor calc. The factor calc is the main contributor to the form, to the shape of the graphs. So looking at this on its own provides a little more insight into whether or not this whole thing works. So factor calc is supposed to be part of the infinite series. So not every term is supposed to look absolutely perfect. It's supposed to combine to work very well. However, at some values of n, for example, n equals 3, that's the one we'll be discussing here, you get a graph that is strikingly similar to the action potential, which suggests that being that this is the main contributor to the form of the graph, the shape, that there is some validity in this solution. Now you may be saying to yourself, that's great, show us some graphs. So I'll get to that right now. So keep in mind that action potentials, they're solitons. When they are composed with other solitons after interaction, basically when they collide into each other, they come out the other side with the same velocity and the same shape. The action potential returns to resting voltage after it dips down. You'll see what I mean in a second. And the dip down must not be of greater magnitude than the peak. And keep in mind, this is not even the full model in action. This is just factor calc. And already it's very similar. So on the left is an experimentally gathered oscillograph of an action potential. And on the right is the mathematical model. A lot of similarities, and we'll discuss them here. So one really big important thing is that it does not blow up in finite time. You can go to either end and it stays at 0, nothing blows up. It's fantastic. So here we have the absolute refractory period. Here you have this dip down I was talking about, the relative refractory period. And here we have where it's approaching the resting voltage from below. The shape meets those basic criteria, works very well. So I don't know about you, but I hope the waves in our neurons are not just standing still. So want to see some moving stuff, things colliding. So as discussed before, solitons, they they have a velocity that stays constant after interaction, and after interaction, shape is preserved. So here's this, and I'm really hoping this will work. Can you all see the movement? Okay, cool. Yes. So let me do it one more time. So the T slider just represents time. This is the waves moving through time. And the numerical values for this aren't really important, as it's mostly just the interaction, the qualitative features of the graphs that I'm focusing on here. And as you can see, they go through each other, they interfere with each other, come out the other side, same speed, same shape. So the purpose of this research for me, I've really enjoyed doing this research, and I believe that after trying to figure out what is wrong with the explosion, as I call it, the chaos explosion, I'd like to call it, trying to figure that out for a while, I think the next step for me is, after figuring that out, definitely working on a more complex version of this, including some more stuff from things like information theory with noise, and trying to create webs of neurons, not just 1 or 2 signals on a single neuron, but multiple neurons interacting, trying to get some more complex behavior from it. And the physically accurate results from this may also prove useful. But honestly, the purpose for me is doing cool stuff with the graphs. And here's my references. And I believe that's it. I'm not sure what the timing on that was, but if it was too short, we have extra time for questions.
So thank you very much. And questions for our speaker?
I just like someone who does research in order to do cool stuff.
I'm sorry, I missed the first few slides, but I think I saw that this is a model based on ODEs, correct?
It's based on partial differential equations.
Oh, it is, okay, yeah.
Yes.
Because this was my question, actually, because clearly the best model here would be based on PDEs, like a Kardashev de Vries equation, something like that.
Yeah.
Yeah. Thank you.
Can you go back up to your second order PDE at the top of your slides?
Sure. This?
Yeah. Okay, so what were you let's see, you were thinking then is that you're saying, let's see if we understand this. So basically you're saying if the theta is and the limit goes to 0, that or if the theta in the limit goes to infinity, then this that's physically the only justification for letting this thing mathematically, the second order t coefficient, be 0. And in that case, it would have just the traditional Hodgkin Huxley system, which traditional in the sense of after the original model, which was put forth by Hodgkin Huxley, did include the second order t, but after the effort to in the thought that it may simplify numerics to go ahead and just include the first order time derivative, thereby making this basically a nonlinear diffusion type equation, that those solutions were hoped then that they would be able to achieve at least better numerical estimate solutions, correct?
Yes, I believe so.
Yeah, okay. So, but what was found, what was it then, is that by only, even up to current day, the great paradox is that even current day that only uses the first order t version, the thing about it is is that the solutions invariably blow up in finite time, except for very special boundary conditions, which in a physical system are actually not very telling of what actually occurs in the biophysics in the actual in vivo situation. So yeah, this what was the can you go down to down to the, I guess the next slide or so, where you have the formula for the solution that was obtained early in the reference? Yeah. So what was that? So basically, you're mentioning about the use of this nonlinear or of this Lagrange inversion formula. So it looks that in this earlier work of that you have here, that it was the formula for the coefficient in that infinite series is actually the Lagrange inversion formula, but for the specialized case of where the point of expansion, the A that you have in your more general statement for Lagrange inversion, where it was based on, at the time of physical considerations, it was thought that by letting that A equal 0, and so this was basically a departure point for doing this. So it may be, from what I gather from what you said earlier or later here, is that maybe instead of, if you go down to your general form for the Lagrange inversion formula, yeah, there. So that basically it may prove in your later upcoming works, maybe, that by using a different A instead of identically letting the A be equal to 0, and I guess by extension that f of A, assuming that it was 0, it may be that by finding a more appropriate point of expansion and including a non-zero f of A, you may actually be able to maybe remove this anomaly that you've demonstrated numerically through Mathematica. Does that basically sound right?
I'm not entirely sure that would be possible. I have a lot of what I actually believe some of the graphs shown here use a non-zero A.
Okay.
But a lot of exploration with different values of A, even making A a variable sometimes, hasn't done a lot. It's definitely changed the shape of the graph for the better. I believe in this case, making A a variable produced some of the better graphs that looked more correct, but I'm not sure whether they'd be more numerically accurate. Most of this is just graphical, qualitative dive into it.
It's very interesting. So what were some of these ideas that you're thinking about for, I guess if you go down to your interaction dynamic graph here, the one where it's moving. So it looks like what you basically got coming in from the left, you've got basically just something that has a different amplitude to start with. And then when they collide, so you're basically saying that if there's different strength of action potentials propagating on the nerve, that those things can transfer through each other without destroying the integrity of the signal, I guess. Is that basically right?
For the most part, there's no such thing as a perfect soliton, obviously, but for the most part, they do retain their form and velocity.
Yeah, you had mentioned also about the inclusion of noise and other lossy factors. The thing about it is, in the physical world, there would also be some loss. There would also be some loss of the amplitude upon collision due to radiative effects of the collision of these solitons. So you mentioned, I think, by extension, that the inclusion of noise effects in here would definitely be an interesting way, because the noise effects would actually account for substrate interference into the target neuron that you're modeling from external electrical sources, let's say, i.e. other neurons. So they can basically see how the coupling effects will definitely have more complex interaction or more complex influence on this, even if you're only looking at these two target action potentials. In other words, if you had this thing being driven by or being influenced, let's say, through the conductance, through the G, and that thing were due to some external field interaction, you can definitely see how this model could be, and the solution could be improved. That's what I'm saying. The work that you cited earlier could be improved by including these effects, making it more physically viable with the biophysics. Thank you.
Any other questions for our speaker? Okay, well, thank you very much.
Thank you.